Okay, welcome everyone to my channel. I am Ansar and I'm your helping hand. Sorry, I don't know if that's cheesy or not, I don't know. Anyway, today we're going to continue our discussion slash explanations on sampling distributions that are related to normally distributed data. So this is part 2. We're going to be talking about the T distribution and the F distribution. Before we get there, however, let's just talk about where we left off. So in the last video, we spoke about the sample mean and the sample variance. And this is what we define the sample mean as. It's just a simple average of all of our observations for our random variables. And in this scenario, I guess, we're assuming that these xi's on the right-hand side of the sum, that is normally distributed. That's the only assumption we have for most of these things, and some other things about independence, but anyway. So this is the sample mean, and we showed last time that xn bar, which is a random variable, because it's can take on a range of values depending on where we get our sample from, or how we sample specifically, or what our sample is. That has a normal distribution with the same mu as the xi's, and then with a variance that's just divided by the number of samples that we took. Okay, so we saw last time that while this xn bar being normal is a good thing, usually the way we use it is by standardizing it, simply because working with a particular normal distribution with some arbitrary mu and some arbitrary variance makes our life difficult, because then we have to integrate a weird looking integral. So instead what we do is we just standardize. So we just take this z thing and we say it's equal to the standardization, which is where we remove the mean and we divide by the standard deviation. And this implies that this c value thing is a normal distribution, a standard normal distribution, or is distributed with a normal distribution with mu equal to 0 and standard deviation equal to 1. So we saw last time that by using this manipulation, by making this c value, or this new random variable called z, that by calculating the probabilities of outcomes of the xn bar statistic, right, it's equivalent to calculating the probabilities of a standard normal if we have some assumptions, if we're given the mu, the population mean and the population variance, right? So in other words, what this means is that we can validate our assumptions of mu and sigma squared, right? Because we can do that by checking whether the outcomes of the c, the standard normal random variable, which we defined above, we can check whether those outcomes line up with our expectations of a standard normal random variable. So for instance, if we get a z value or a z score of 0 or 0.5 or 0.2 or -1 or -1.2, those kind of are in the realm of possibility that we accept as being likely. Getting a z-score of something like -100, which we saw in the last example with the quality assurance officer, that's very unlikely. So our assumptions must have been off by some factor, or basically it tells us that our assumptions are not necessarily as accurate as we think they are, because we got this very, very unlikely number for the z value, or the z-score. Okay, so that was the sample mean. And then for the sample variance, we said that s squared, or in previous videos I called it s squared with a subscript with an n. I've taken that away, and you'll see later why I do that. But basically, you just have to think of the s value as being the sample variance, and I mean s squared as being the sample variance. The subscript n usually denotes the number of samples that you've taken, but later on it's going to denote something else, so that's why I've removed it here. But basically this is just we're taking all of our observations and we're looking at how much it deviates from the sample mean. So we're taking all of our observations, subtracting xn bar, squaring that whole thing, adding all of those up, and then dividing by n-1. There's reason, once again, that we divide by n-1 and not by n. I can make a video about that if you are interested in why that is the case. let me know, but it's not super important. We just have to know it's n minus 1. Anyway, so this statistic, should say statistic, not statistics, but this statistic has a distribution that's related to the chi-squared distribution. It's not, so a squared isn't actually a chi-squared itself, but if we manipulate it a bit, where we multiply by the number of sample points we took, -1, and then divide by the population variance, then that has a chi-squared distribution with n-1 degrees of freedom. Okay, so once again, by using this manipulation, we calculating the probabilities of outcomes of the statistic for our sample variance for a squared is equivalent to calculating the probabilities of some chi-squared distribution with n-1 degrees of freedom if we have some assumption about the population variance. So in other words, we can validate our assumptions of sigma squared by checking whether the outcomes of that statistic manipulated line up with our expectations for that should not be a standard normal, but that should be for a chi-squared with n-1 degrees of freedom. Okay, so where does that leave us? Well, we have the sampling distribution to validate our sigma squared assumptions by itself, right? So if we have some assumption about sigma squared, we have the sampling distribution that can either give us feedback on our assumption, or we can validate our assumption, or alternatively, we can use it to get information about sigma squared, right? Using this sampling distribution with chi-squared n-1 degrees of freedom, right? So that's fine for sigma squared. We can work with sigma squared. And we kind of have a sampling distribution for mu, right, to validate mu or to get information on mu, right? We've got the square root x n bar minus mu over sigma squared as a standard normal. So it's kind of a sampling distribution for mu. Well, I say sampling distribution for mu, that's not what I mean. What I mean is that this sampling distribution for square root of n x n bar minus mu over sigma being a normal distribution, that sampling distribution kind of gives us information about our mu assumption, but because there's a sigma there, which is our standard deviation, which is our sigma squared, that doesn't really help us because that's two assumptions we're making. So basically that sampling distribution has variance built in or standard deviation built in. So in other words, in order to validate or get information on mu, we need an assumption about mu and sigma squared, and sigma. Sigma and sigma squared are kind of equivalent. You just have to square root sigma squared to get sigma, right? So what this means is that when we want to do, when we want to make inferences about mu, right, unless we also have sigma squared, making inferences about mu using this particular sampling distribution of square root of n x n bar minus mu over sigma, it's not that useful or less useful than something that just depends on mu. So we want to be able to get information or validate our assumption for mu using only the assumption for mu itself. We don't want to have to validate our assumption for mu based on our assumption of mu and our assumption of sigma squared. Okay, and that's where the t distribution comes in. Okay, so the t distribution, it's also called student t's distribution, and the history behind the name has to do with someone called William Gossett. He used to work for the Guinness Beer Company. There's a whole story behind it. He wasn't the first person to discover it, but he kind of got, well, most of the credit because he was English, essentially. Well, and other reasons, but essentially he discovered it later than other people, so people had discovered it beforehand. Anyway, we're not here for a history lesson. The t distribution isn't just one distribution, it's actually a family of distributions, and it's parameterized by one parameter, which is degrees of freedom. So it's similar to a chi-squared. Chi-squareds also have degrees of freedom, t-distributions have degrees of freedom, and that's the only parameter that parameterizes it. So we don't have two parameters like in the normal where we have a mu and a sigma squared. Okay, so that's just saying x is distributed according to the t distribution with n degrees of freedom. So that's how you would write it out. Okay, So it's not necessary to like know what the CDF of T is, what the PDF, what the MGF is. It's actually, well, the MGF is doesn't exist, the PDF is ridiculous, and the CDF is also ridiculous. So like you don't have to know it. It's not important. It's not a random variable or a distribution that you need to know like the actual information about the distribution. It's more how we use the distribution. So what is important is how do you get a t-distributed random variable. So the t-distribution, basically a t-distribution and the f-distribution, and I mean, I guess you could say other distributions as well, they have this property where essentially if you take some, I'm going to say, recipe of other random variables with other distributions, if you take some recipe of other random variables and you put them together in some kind of very specially calculated way, then you will get another special kind of distribution. It's similar to how in term 1 we said that, you know, if you have a gamma distribution where your alpha is equal to 1, then that's just an exponential with the same beta. Or if you have an alpha of n over 2 and a beta equaling 2, that's a chi-squared with n degrees of freedom. So it's similar to that, but it's different because we're no longer talking about the parameters being the thing that determine like the connections. We're now talking about actually just taking different types of distributions and combining them in a way, to get another distribution. So the way we get a normal t-distribution is, let's say we have a standard normal, right? So we have some standard normal with 0 and 1, and I want to stress this, we can choose any way of generating a standard normal. So we can choose whether we've got a normal distribution and we standardize it, whether we've got a, I don't know, a chi-square distribution and we square root it. I think that works, I don't know. But essentially, if you have a standard normal, then you can continue with the rest of this thing. So you need a standard normal and you need another chi-squared. So you have a standard normal, right, with 0 and 1, that's the standard normal. And then you have a chi-squared with n degrees of freedom, right? Then if z and v are independent, so if those two random variables are independent, then the following recipe or combination of z and v will give you a t-distribution. So what you do is you take z and you divide it by the square root of v divided by the number of degrees of freedom that v has. So if t is equal to z over square root of v over n, then this t thing, this combination that we have, is a t-distribution. Now, I wouldn't expect us to be able to know how to prove it or why this is the case. I think that in general, no one, I mean, I'm not going to say no one knows why it's the case. William Gossett knew, and he published a paper back in the day, and we've been using it ever since, so it must be important. So I just want to point out something here, which is that I want to point out the relationship between Vn and the degrees of freedom of the t value, right? So capital T is the random variable, right? And its distribution is a t distribution. I said capital T and small t, maybe that was a bit silly because it's not confusing. Regardless, what's important to note is that the chi-squared that we have, the v, we need to divide by the number of degrees of freedom we have in our chi-squared, and then we will have the same number of degrees of freedom in our t distribution. That's important because later on we won't be working with n degrees of freedom, but we'll be working with n minus 1. I just want to quickly show you what a t-distribution looks like. It's very closely related to a normal, and by closely related, I mean it looks like a normal distribution. It just has fatter tails, which means basically there's more probability that things are in the tails of the distribution. So here you can see what the different, here v is the number of degrees of freedom. So we can see that as v increases, this little peak of the distribution goes up and the tails go down. And essentially what happens is that as n, which is your degrees of freedom, or as v goes to infinity, then your t distribution will be a normal distribution. Yeah, so that's the t distribution. But, you know, we've got all this normals and this chi-squareds. There's, I mean, what's the use of it? Well, the use is that we have certain statistics that are distributed normally, and we have certain statistics that are distributed related, or the distributions are related to chi-squared, so we can generate our own t. So generating a t-distributed random variable. So just going back, a lot of the times I will kind of switch up letters. And the reason I do this is just so that I kind of want you guys to be able to see that the letters that we use have absolutely no real meaning to what they mean. So you do need to be comfortable with letters changing from kind of scenario to scenario. Obviously, within a particular explanation, I won't change the names of the random variables, but the actual names of the random variables that we choose, that's just anything. Okay, so if we have a standard normal and a chi-squared with n degrees of freedom, if we take the standard normal and we divide by the square root of this chi-squared divided by the number of degrees of freedom that the chi-squared has, that particular function will have a t distribution with n degrees of freedom. Went through that quickly because I said it earlier. So we have a standard normal, right? We know that if we take our xn bar, subtract our mu, divide by our sigma squared, and multiply by the square root of the number of samples we get, that is a normal distribution. We know that that's a normal distribution. We kind of got that derivation in the last video. There is a proof, and I will link to it, so you can go and watch the proof. But this is a normal distribution. So this is our z, essentially, or this z value is equal to a in the line above. Okay. Then we also have a v. We also know how to get a chi-square distribution. If we take our sample variance and we divide by our population variance and we multiply by the number of samples, we have -1. Then we have a chi-squared with n-1 degrees of freedom. Okay, so we then have the following equation. So if we take our standard normal, right, and we divide by the square root of any chi-squared, right, divided by its degrees of freedom, that's distributed according to a t distribution. Now we can just plug in what our z is and what our v is and do some manipulation. So you can see there at the top we've got the z, and at the bottom in the square root I kind of put v over to one side, and then obviously dividing by n-1 is the same thing as multiplying by 1 over n-1, and then the n-1's cancel, which leaves us with this. And then what you can do is you can just take the square root of s squared and the square root of sigma squared, and that will become s over sigma. And then because we're dividing, it's the same thing as multiplying by the reciprocal. I'm kind of going through the algebra quite quickly because I assume that being in a math stats second year course at university, you understand how algebra works. But if you don't, I would suggest brushing up on fractions. So that's equal to this little thing over here, and then the sigmas cancel out, and we are left with the penultimate formula for a t distribution. So this t distribution that we have here at the end, right, the square root of n xn bar minus mu over s, looks incredibly similar to our initial definition of z, right? So our z value is the same numerator, it's still square root of n xn bar minus mu, but in z we're dividing by our sigma, right, our population standard deviation, but in our t value, which is root n divided by s, we're dividing by our our sample standard deviation. So there's this kind of relationship between z's and t's where our z score, or our z value, is our sample mean minus our population mean divided by our population standard deviation, but our t value is our sample mean minus our population mean over our sample standard deviation, right? So there's this relationship between the two, and it's kind of, if we look here, right, if we think about how S and sigma are related, right? Sigma is our population standard deviation, and S is our sample standard deviation. So our sample is kind of an estimate, right? And we haven't really got into estimators yet, but anyway, S is our estimate for sigma, right? And we kind of have this intuition, I'm going to say everyone kind of thinks that the more samples we take, right, so the larger our n value gets, the closer our estimate should be to the true value. So the more samples we take as n gets bigger and bigger and bigger, S, or S squared, should get closer to sigma or sigma squared. Now, if you look at, just go back to, I can't go back, but if you remember the kind of how it looked, the PDF of a t-distribution, we saw that as n goes to infinity, the t-distribution looks like a normal distribution. And if you think about what n being infinity means, it means our sample size is infinite, which means we've essentially sampled everyone in the population, which means we no longer have a sample variance, we do just have the population variance. So that kind of makes sense that as n gets bigger, S gets closer to sigma, and so this t thing that we have over here, which is a t distribution of n minus 1, will look closer and closer to a z value, or a z-score of a standard normal. Okay, so that's distribution. Now we kind of want to go, why is this useful? Why do we need this? Well, if we look at the formula for a t-score, or a t-distribution, we'll call this t thing, this root n over whatever, it's called a t-score. And if we look at the t-score, this is another sampling distribution for xn bar that just depends on mu. Okay, because S is the sample standard deviation, which is a value we can calculate. It's not a value we assume, right? When we had our z-score, we had this xn bar minus mu times by square root of n over sigma, and we had to have an assumption for sigma, whereas now we don't have an assumption for sigma because we just have our sample standard deviation. So we don't need an assumption, which means the t-distribution is useful, right, for getting information about or validating our beliefs about mu in a way which does not need an assumption about sigma squared. So the other reason it's useful is that the probabilities for t distributions are tabulated, which just means that you can go into the back of your textbook and look at a table for t-scores, and it will give you the probabilities of a t-score being above a certain value or below a certain value. And so what that means is that when you go and get an xn bar, right, when you go and sample something, and you have an assumption about what your population mean is, when you go and sample and you get a sample mean and you have a population mean assumption, and you calculate your sample mean and you calculate your sample variance, and you create this t-score thing the way we have currently defined it, then you're going to get a value for a t, which you can go and check what the probabilities of that t value occurring is. And so essentially, you can basically what that means is that calculating the probabilities on this t-score, or the x root n over s times by xn bar minus mu, that's the same thing as calculating probabilities on a t-distributed random variable. And so we can use the t-distribution to get feedback on our assumption for mu without needing an assumption for sigma squared. And so that's why the t-distribution is useful, and that's why we use it. And you'll see later on in the course, we will get very, very acquainted with t-scores and the t-distribution. Okay, so up until this point in time, we've kind of been talking about, like one particular sample, going out and doing one sample, and then that's it. And then we come in and we do our statistical inferences, and it's got to do with one particular group or one particular sample. So what happens if we have two samples, right? So let's say we have two sets of data which we want to, I'm going to say compare, but we could also just say analyze, right? So you can think of two different years, right? You can think of a first year class and a second year class in terms of their height. You can think of, 2015's rainfall versus 2020's rainfall. You can think of 2020's average temperature versus 2000's average temperature. You can think of different countries. So essentially, anytime you have two different sets of data, right, how do we go about comparing that? Well, one natural question is, do they come from the same or similar populations? And what I mean by that is, is the distribution for, let's say, first year heights, right? Is that the same distribution as second year heights? And you might think, well, 1 year difference, it's not all that big when, you're talking about people that are, past the age of puberty. So, we've kind of done most of our growth physically, not mentally. But you might assume that, hey, these seem like similar populations, so they might have similar distributions for their heights. If you think about the average temperature for, let's say, Cape Town in 2020 versus the average temperature in, let's say, Sweden, or a city in Sweden. I don't know what a city in Sweden is. Let's say Copenhagen. Copenhagen, I know, is in Denmark. But if we think about those two cities, well, we might assume naturally that the two populations, or the two distributions of temperatures, those are very different because, they're two different climates, whatever. So we want to ask ourselves, do these two samples, do these two data sets, are they coming from similar or the same distribution? Okay, so are the distributions similar is the same thing if you're asking about whether they're coming from the same or similar populations. So there's multiple ways to check this. You can check if the CDFs are equal for a particular population. You can check if the MGFs are equal, if they exist for two different populations, and then you have more advanced options, things like characteristic functions and other things, which we won't go into. But there is one important point here, which is the second point. So if the MGFs exist and if they are equal, right, then it implies that mu, because mu is just the first derivative of the MGF evaluated at 0, right, and if the MGFs are equal, then that value should be the same thing. So if the MGFs are equal, it implies that mu is equal, and it would also imply that sigma squared is equal, because our sigma squared is just equal to our second moment minus our first moment squared, and the second moment is just the second derivative of the MGF evaluated at 0. So those two things would also be equal, right? If the MGFs are equal, our mu and our sigma squared would be equal, and so would the rest of the moments, technically, but for now we consider the first two because it's usually just easier to check two things, and if those are not equal, then the rest are definitely not. So we think about, let's say, one sample we subscript by a 1 and another sample we subscript by 2. So if the means are the same, if the population means are the same, that implies that mu1 minus mu2 is equal to 0, right? Now, the difference, and I'm going to kind of, I talk about the difference of two normals. Now, the reason I talk about the difference of two normals is because, one, we're kind of assuming that our data is normally distributed, but also in terms of sampling distributions, the sample distribution for our estimate of the population mean, which is the sample mean, that sampling distribution is also technically a normal distribution. So we kind of want to think of our sample mean and our population mean, so xn bar and mu, those two things are related to each other, and so their distributions are related to each other. So if we have these two means that are the same, their difference should be equal to 0, and the difference of two normal random variables still has a normal distribution. So essentially we're fine on this front. We can work with it. We can do difference of means and difference of sample means and still do like the same kind of analysis that we had earlier, and we can still use a normal distribution or a t-distribution depending on whether we have assumptions for sigma squared. But that's fine, right? That's kind of okay, cool, whatever. However, our sigma squareds, if those are equal, that does imply that the difference is equal to 0. Now, remember we said earlier that the population mean and the sample mean are related, and so their distributions are related. So a normal distribution of sigma squared, a normal distribution for our population mean, our mu's, and our normal distribution for x in bars, they're related. The same thing kind of applies for sigma squareds and s squareds. So our sigma squared, we can kind of relate to a chi-square distribution, essentially. And if we have this equality of our sigma squareds, right, if we want to check whether these two things are equal, then that implies that the difference is equal. However, the difference for two chi-squared random variables is not a chi-square random variable. It's very easy to check that because a chi-squared random variable is always positive. And in this case, we might have that sigma squared 2 is bigger than sigma squared 1, and so that's not going to be a positive number, that's going to be a negative number, so it can never be a chi-squared random variable. So we have a problem, right? Now, the fact that our sigma squareds are the same, besides implying that the difference is equal to 0, it also implies that the ratio is equal to 1. Now, the ratio of two chi-squareds is related to a famous distribution. I capitalized the F in the famous distribution because it's related to something called the F distribution. Now, what is the F distribution? Okay, so it's the same kind of process that we had for the t distribution, where it doesn't really matter where the F distribution comes from. It's just what's important about the F distribution for our situation is how do we get there, all right? So now let's say we have some chi-squared random variable with n1 degrees of freedom, okay? That's important. The degrees of freedom of a chi-squared random variable is very important, and especially in this scenario because we're going to do a lot of manipulation. But let's say you have one chi-squared with n1 degrees of freedom, and then you have another chi-squared with n2 degrees of freedom, right? Then if you take your chi-squared, your first and then there's another requirement that A and B need to be independent. So then if you have all of these criteria met, right, you have one chi-squared with n1 degrees of freedom, and you have another chi-squared with n2 degrees of freedom. Then if you take A, right, and you divide it by the number of degrees of freedom that it has, so if you take A and divide by n1, right, and you take B and you divide by n2, and you take the ratio of those two things, then that has an F distribution with n1 degrees of freedom and n2 degrees of freedom. So you'll see the F distribution is a ratio of a chi-squared divided by its degrees of freedom and another chi-squared divided by its degrees of freedom. And it's important that your n1 and your n2s match up. So essentially the number of degrees of freedom in the numerator's chi-squared is the first parameter, and the number of degrees of freedom for the second chi-squared, or the denominator's chi-squared, is the second parameter. Okay, so here where n1 is the degrees of freedom in the numerator and n2 is the degrees of freedom in the denominator. Okay, so this is just the kind of like, what is an F distribution? Well, it's just the ratio of two chi-squared distributions scaled by the reciprocal of their degrees of freedom. That's what an F distribution is. You don't need to know it's CEF, you don't need to know it's PDF, you don't need to know it's MGF, not important. Yeah, all that's important about the F distribution is that if we have two chi-squared distributions, or we have two chi-squared random variables, we can create an F distribution out of it. Now, we can go and generate that any way we want, and the way we're going to generate it is the following. Okay, so I'm just reiterating what a chi-squared is. Q is chi-squared within Q, R is chi-squared within R, so then F is equal to Q times by, or Q over NQ, and R divided by R divided by NR. It's a lot of divisions and fractions. Like I said, you need to get used to and be comfortable with fractions. That's an F distribution. So imagine we have, and that's meant to say 2 with a W and not just an O, but anyway, imagine we have two independent samples, right? And the reason we need independent samples is because that's how the F distribution is defined. Then we have this, if we have an independent sample, right, then the way we can generate a chi-squared out of one of those independent samples is by taking the sample variance, right? And I've subscripted everything with a 1 to say this is for sample 1. So if we take our sample variance, divide by our assumption for the population variance, or if we know what the population variance is, if we divide those two things and then divide by the number of samples we took -1, then that is a chi-squared with n minus 1 degrees of freedom. Okay, just as well for the second sample, but everything is subscripted by 2. So then we have the following, right? Then that thing over there, which you'll just notice is a chi-squared divided by the number of degrees of freedom for the first chi-squared in the numerator of this big fraction, and then in the denominator of the big fraction is the second chi-squared, or the second sample's chi-squared thing, and it's multiplied by 1 over the number of degrees of freedom that it has, right? So all we're doing is we're just taking this chi-squared for one sample, dividing by another chi-squared for another sample, and then we do some manipulation, and that's just equal to S1 over sigma squared, that's equal to S squared 1 over sigma squared 1 divided by S squared 2 over sigma squared 2. And all this means is just we take the sample population, the sample variance for the first sample divided by the population variance for the first sample, divide those two things. Then we take the sample variance for the second sample and the population variance for the second sample and divide those two, and then divide those two numbers, right? So that's just equal to the following, right? It's equal to, when you have one fraction divided by another, it's the same thing as the first fraction divided by the reciprocal of the second. Okay, so that's just an F distribution, and what's important here though is the degrees of freedom. So the degrees of freedom for the F distribution is the number of the sample size of the first sample -1 in the numerator, and then the sample size of the second sample -1 in the denominator. So that's why it's n1 minus 1 first and n2 minus 1 second. Okay, so that's just kind of the brief outline of the F distribution. Why is it important though? Okay, so we have this whole thing over here, and it's equivalent to this other thing on the other side of the right arrow. I'm just doing algebraic manipulation at this point in time. There's nothing fancy here. Okay, so basically what we have is a ratio of two sample distributions, sample variances. So we have the ratio of two sample variances, and we're multiplying it by the inverse of the population variances. I say inverse because, you know, the ones need to kind of be grouped together and the twos are grouped together. So anyway, that is an F distribution. Okay, so if we want to know whether two samples come from the same population, right, then the ratio of the population variances, so that's sigma squared 2 over sigma squared 1, if we're assuming that these come from the same population, then that value should be equal to 1. Okay, which leaves us with the following. squared 1 over s squared 2, where 1 and 2 is the first sample, where 1 is the first sample and 2 is the second sample, that's also an F distribution, because we're assuming that the ratio of the population variances should be equal to 1 if we think that our populations are the same. Okay, so we have this ratio of sample distributions. Now, what that means is that we go out and we calculate a sample variance and for one sample, and we calculate the sample variance for another sample. So calculating the ratio or calculating probabilities on the ratio, i.e. calculating what's the probability of seeing this ratio being equal to a certain number, is equivalent to calculating the probabilities on a random variable with an F distribution where they have the same degrees of freedom. So basically that means that because the F distribution is tabulated, which means we have probabilities for the F distributions, we can find the probabilities of seeing the ratio of sample variances being equal to a certain number, and we can validate our assumption for our sigma squareds, right? So, well, yeah, so we can validate our assumption about whether our sigma squareds are equal to 1, the ratio of them are equal to 1. So it's useful in the sense that anytime we want to validate a relationship between population variances, because well, anytime we want to validate a relationship between population variances, we can essentially do that using the sample variances. So we want to validate our assumptions on the population variances, and we do that by looking at what the ratio of the sample variances is, and the way we do that is by looking at the probabilities of the ratio of the sample variances, because the ratio of the sample variances has the special distribution called the F distribution. Now, we assume that the ratio between the population variances is 1, right? We assume that they're the same because we wanted to check if these two sets of data come from the same population. So basically we're assuming that the population variances are the same, which means that the ratio is equal to 1. But this kind of analysis is just as useful for the assumption that the population variance for one set of data is twice as big as the other population variance, or any other ratio for that matter. Okay, so that was a very long explanation for the F distribution, the T distribution. The other thing is that the F distribution is used in ANOVA, which is analysis of variance, and that's all about determining whether data sets come from the same population. Now, I've kind of did a whole explanation of everything with regards to the T distribution and the F distribution. We won't really see why it's useful. I mean, I've explained why it's useful, but we won't use this usefulness until we start getting into confidence intervals and hypothesis testing, and for the F distribution for analysis of variance. So it's kind of difficult to see the forest for the trees at this point in time, because essentially I feel like I'm doing the exact same thing that I tried not to do or explained I didn't like, which is, everything just kind of being dumped on you. But I hope that the way I've explained it at this point in time is a bit easier than just kind of seeing all of these formulas, and that knowing that the T distribution is useful because we can validate our assumption for X and bar or we can validate our assumption on mu using just mu or just the population mean rather than having a sigma squared assumption as well, and then knowing that the F distribution is useful because it helps us validate whether ratios of population variances are the same. I hope that kind of makes sense. And yeah, that's the end of this video. Please like and subscribe, comment if you have any questions, and let me know what else you guys want to see. I think that the next video that I will be doing will probably be on the central limit theorem, so stay tuned for that. Cool beans, bye!